Hey guys, I wanted to give you a follow-up lesson to the one that Mr. Duffy gave last week about saturated, unsaturated, and supersaturated solutions. You guys were able to look at some solubility curves and kind of draw some conclusions about that. I wanted to follow up with that and talk about something that actually has a lot of really important applications in everyday life. There's not going to be a worksheet that goes along with today's lesson, but later on this week I'm going to give you a sort of a numeric description of solubility, one where we can kind of calculate solubility and learn some units for that as well. So he talked about earlier this week, Mr. Duffy talked about saturated versus unsaturated solutions. One is, there's going to be sort of leftover solid in the saturated solution just because the solvent, in this case water, can't hold any more of whatever you're trying to dissolve. But an unsaturated solution, you haven't reached that maximum. And so we can kind of look at a solubility curve. Anything above the line or anything on the line is saturated, meaning that's the maximum. That's how much you can dissolve. But anything below the line means that it could hold more. So for a lot of salts, as you heat up the water, you can dissolve more and more of the ionic compound. And some compounds are really affected by this. Like a lot of the nitrates, like sodium nitrate and potassium nitrate, you can go from dissolving almost none, like 5-10 grams in ice water, 0 degrees, up to 200 grams at just relatively warm water, 60, 70, 80 degrees. So this is very strongly affected. One that's not affected very much, coincidentally, is salt. Regular table salt is not really affected by water or by the temperature very much. If you heat up regular water, you can't really dissolve much more regular table salt, whereas sugar and a lot of the nitrates are strongly affected by temperature. One thing that Mr. Duffy mentioned, but we haven't really thought of a lot, is what do gases do? Gases have a really high molecular movement. The gas molecules move around a lot more than solid molecules do. They have a lot more freedom to move around. And so when you warm up water, you're going to dissolve less and less and less gas in it. And as you approach the boiling point of the water, you can dissolve basically no gas. This is something you might notice you notice in the wintertime when you turn on the water and the water is really cold outside and it comes into the house and you notice the water looks like it's almost like foggy with bubbles. One reason that can happen is if the water is really cold, it dissolves a lot of air, and then when it warms up inside the house, you see those bubbles kind of come out. I notice this when in the morning when I heat up coffee that's been sitting out for a little while. It's kind of like lukewarm. If I heat it back up, what happens? The solubility of the air and the nitrogen and whatever that's dissolved in it goes down, and those bubbles start to come out. And so I notice I get some bubbles on the surface of my coffee, not because it's boiling, but because the air that's dissolved in it is coming out. Another thing I wanted us to think about is, what does pressure have to do with this? So if you think about pop, we talk about like carbonated water. Pop has a certain amount of carbon dioxide that's actually dissolved in there. Now, carbon dioxide we know is a gas, but you can dissolve it in liquid, and then it turns into carbonated liquid. When you first open a can of pop, that pressure is released, and the bubbles want to come out of the pop or out of the soda. And so you can say that once the pressure is released, there's pressure inside the can. Once you release the pressure, the bubbles want to come out. But another way that another reason it holds the fizz a little bit better is if you keep it cold. So if you warm up a can of soda, what ends up happening is it just is going to go flat regardless. And I used to do a lab with my chemistry students, which we would be doing if we were in school right now, where we can measure the amount of gas that comes out of soda. And I always bring in like a 24-pack of Dr. Pepper, and you just see how much gas comes out of it, and you realize that as the pop gets warmer, it releases a lot more of the carbon dioxide at a lot faster rate. The only way that you can keep the bubbles inside there, the only way that you can keep the carbon dioxide dissolved is if you put it under pressure. Oh, we'll come back to this in a second. So, pressure is really important for keeping those gas molecules dissolved. If there's a lot of pressure inside the gas part of a bottle or a can or whatever, the gas is essentially being forced into the liquid and it dissolves because the pressure is, remember, pressure is the force that it's hitting the surface with. So high pressure means high force, that it's forcing molecules under the surface of the liquid. If the pressure is released, what ends up happening is those can freely move out of the soda, and that's what we see as fizz. So when the bottle's still closed, they're actually just dissolved and it looks all peaceful and calm. But when you release that pressure, the bubbles, the gas can come out of there. This seems like, okay, pop isn't really that important. What does this have to do with, something that actually matters? Well, one thing that really matters with this is a situation that scuba divers can encounter that's called the bends. So I've had this, actually my friends have told me stories about the bends and how they've almost gotten it or how they've had friends that had disasters with the bends. This is what happens typically. When you first get in the water wearing scuba gear, maybe you're on vacation or something like that, you get in the water and the air that you're breathing, you have a pressure regulator on the tank that you're breathing with, is feeding in air into your lungs at just atmospheric pressure at the surface. Since water weighs a lot, when you go down under the water, you actually increase pressure very, very, very quickly. And so you might only need to go 30 or 40 meters down, and at that point, the pressure on you is 7 times what it was at the surface. So in order to get the air actually into your lungs, because there's a lot of force on your lungs, in order to get the air in, the pressure on your tank needs to increase to force the air into your lungs even harder. Maybe at the bottom of the ocean, or at the bottom of whatever you're diving for, we'll say 7 atmospheres. So that means that the air in your lungs is really high pressure, and it's dissolving in your blood at really high pressure. Think about the pop bottle. Putting a lot of pressure, that gas is dissolving in your blood. Your blood is a liquid. You have plasma in your blood. It's dissolving. Okay? So what's going to happen to Scuba Steve when he tries to go back up to the surface is he's going to have a high pressure gas in his blood, much higher pressure than the pressure around him at the surface. So if he goes to the surface too quickly, what happens is the gas in his or her blood just comes out like bubbles in soda. So you can think about the bubbles coming out of the soda just kind of frothing up, and because the pressure isn't there to keep them dissolved anymore, when you come back to the surface too quickly, the bubbles come out. So how do you prevent this if you're scuba diving? If you're coming back up, wouldn't the high pressure gas always come out of your blood? Well, what you have to do is they have like checkpoints, and you have to stop at certain areas on your way back to the surface where you allow the gas to be released from your blood over time. And it turns out that nitrogen and oxygen have varying degrees of solubility, and so you change the regulation where you're breathing more oxygen and less nitrogen at depth to kind of purge your body of the high pressure gas. And you make several stops on your way back up. So you don't come back up to the surface when you're out of air, because if you did that, you just get the bends. What you have to do is you have to wait till you still have some gas left to sort of purge the high pressure gas out of your blood. I had a friend that went scuba diving, and what you do is you wear weights when you're down at the bottom. The weights sort of counterbalance the air that you're bringing down. And what happened was he was looking at something under the water. I can't remember what it was. And one of his weights came loose. So he had nothing to hold him down. And what happened was he just rose to the surface really quickly. And he said he he was terrified of getting the bends. What can actually happen is you get these terrible bruises, and you can actually die of the bends. I have a link here if you want to watch this about how you can treat this. But it's really quite a scary thing, and it can you would go be in the hospital if you had the bends. It's also called decompression sickness, but kind of a scary thing that can happen when you lose pressure too quickly after you've been in an area of high pressure. The gas all comes back out. But my friend was okay. He what he did was he said he swam as hard as he could toward the bottom, so that even though the weights were trying to lift him, or even though his air tank was pulling him up, he tried to spend as much time as he could away from the surface, and he actually managed to do it slowly enough that he didn't have any severe consequences from that. So he ended up being okay, but it's a thing that scuba divers worry about most often. Another sort of goofy thing I want to talk about dissolving gases. Carbon dioxide is one that's really has a major effect on our environment. Carbon dioxide, we know in pop it dissolves really easily. And actually, carbon dioxide is one of the things that makes pop acidic, because when carbon dioxide dissolves, it turns into carbonic acid. And you can actually taste the difference between carbonated water and uncarbonated water, because the fizz does actually chemically change the water. So carbon, if you drink like Perrier or something like that, it chemically is different than regular water because you have carbonic acid in there, which gives it more of a little bit more of a tangy, acidic taste, which actually tastes better. Most people would agree that acidic foods tend to taste better.
This is bromothymol blue mixed with water. We're adding carbon dioxide from the student's breath. You can see it changing color.
So what does this have to do with the environment? Well, you probably are aware that there's more and more carbon dioxide in the air than there was 100 years ago or 150 years ago. So what's happening to the oceans is that as the percentage of carbon dioxide in the air increases, remember there's pressure in the atmosphere, it dissolves. So that carbonic acid, what it does is it actually turns the ocean acidic, and it sort of bleaches the reefs and things like that, just with a small increase in carbon dioxide. It turns out that a lot of the coral reefs are dying off because of carbon dioxide now. It's acidifying the ocean. It seems like it's a really small amount of CO2, but it actually has a pretty significant effect on our oceans. And so a pretty big environmental impact comes from CO2 in the atmosphere. In the next lesson I want to give to you later this week is about actually calculating how strong or how much of something is dissolved, which we call concentration. And we're going to talk about 2 or 3 important units for concentration, which you'll use in any sort of nursing or medical field to be familiar with. So those will be the last topics of the solutions chapter, and then we'll sort of get prepared for a little quiz on solutions.